Okay, now I'm going to go over an example where we use conservation of momentum. And here this problem is we have a hopper that is filled with sand, and there is sand falling out of a chute on the bottom, and that sand is then being transported by a conveyor belt. Okay, and so we know m dot of the sand that's falling down. We know the density of the sand. Okay, and you could consider that we know the cross-sectional area of the chute. Okay, and what we are asked is, and we also know the belt velocity. Okay, and so essentially we have sand raining down on the conveyor belt, and it's being conveyed away at some belt velocity to the right. Okay, that's being turned by the pulley. Okay, and what we are asked to find is the belt tension required to pull the belt. Okay, and we are to neglect friction. Okay, and so we have our system here, and there are multiple ways to solve this problem. And the strategy that we are going to do is we're going to choose a control volume, because sand is like a fluid. So we're going to choose a control volume that is guaranteed to encompass the entirety of the sand pile. Okay, so we're going to choose a very long control volume that contains the sand, so that basically both of the vertical sides of our control volume do not have any sand in it. So and so essentially, as time goes on, there will be more and more sand inside of this control volume. So this will be an unsteady problem, and we will have also we are going to assume uniform flow on the portion of the control volume where there is sand falling down through the control surface. Okay, and so we'll just write those assumptions down. So 1, I'll assume uniform flow. 2, we will also assume that basically any sand that goes inside of our control volume will instantly move at the belt velocity. So all sand in the CV moves at V belt instantly. Okay, and I'm just going to call V belt VB, and that's in the I hat direction. Okay. 3, and I brought this up earlier, the CV is large enough to contain all the sand. 4, negligible weight and friction. Okay, and 5, a stationary CV, and that implies that the relative velocity Vxyz is just equal to the sand velocity, really. And 6, impermeable wall. Okay, that is, we are neglecting any holes that may be in the conveyor belt, so there's no sand that is falling through the conveyor belt. Okay, and so for the solution for these types of problems, your first step is almost always to start with conservation of mass, and so that is exactly what we will do. So for the solution, we will first start with conservation of mass. Okay, so we'll start with that. And as I've mentioned before, I like to write the conservation equations in their full general form. So conservation of mass is partial t times the integral over the control volume of rho dv plus the integral of the mass leaving through the control surface. So that's v xyz dot n hat dA, and that is equal to 0. Okay, so this problem is not steady, or it's unsteady, so we cannot cross out this term here. We can simplify the relative velocity, because vxyz equals the fluid velocity minus the control surface velocity, which that is equal to 0, and so this equals just the fluid velocity. Okay, and I suppose we could have a seventh assumption that the air mass is negligible. Okay, so that is in our control volume. We do not really need to consider the mass, because sand is extremely heavy compared to air. Okay, so then the integral, we can also simplify this integral then. The integral of rho dv in the entire control volume is just nothing more than the mass of the sand, and I'll call that ms. Okay, so now we can work with these terms here. We have these two integrals here, and we need to evaluate them. And in order to evaluate this one, we do need to draw a control volume. So we always draw that. So I draw the control volume here. So we have our control volume. And just for reference, we have the conveyor belt right here. Okay, and so we do have a couple pieces to the top here. We have a portion here, I'm going to draw that in a different color, where the sand is falling through. And I'm going to scooch this down a little bit to give myself more room. Okay, so we have this portion here where the sand is falling down. Okay, and inside we will have our little pile of sand. And again, we are choosing this right edge of the control volume to be wide enough that the control volume contains all of the sand that has fallen through at any given instant of time. Okay, and so now what we'll have here falling through is some sand velocity that's going down, and that'll be down in the j hat direction, and so that's in the negative j hat direction, equals vs, and we'll have some normal vector n hat, and that will equal j hat, basically pointing up. Okay, and so and we have the sides here. There's no sand crossing them, and we have this portion of the top here. There's no sand crossing that. And we have this bottom here where there's also no sand crossing because we are assuming that the conveyor belt is impermeable. Okay, and so now we got our control volume. We have all of the relevant velocities labeled. And so now we just need to form this integral right here. Okay, and so the integral over the control surface of rho v dot n hat dA equals the integral over this piece here. I'll call this piece 1. I'll call these pieces here 2, and I'll call that piece here 3 at the bottom. Okay, so we have the integral over A1 rho V1 dot n hat 1 dA1 plus the integral over A2 of rho V2 dot n hat 2 dA2 plus the integral over A3 rho V3 dot n hat 3 dA3, and I should be careful here. This would be rho 3, rho 2, rho 1. Well, I just argued here that that the conveyor is impermeable, so there's no mass crossing through it, so impermeable. So that goes away. And there's simply no sand crossing any portion of the second edge on the control volume. So that goes away. There's simply no sand. Because remember, we are neglecting the air mass. And so the only portion of the surface integral here that matters is this piece here, and this here, and we can actually make a simplification here already because we are given that we know the mass flow rate of the sand coming down. Okay, so we know the mass flow rate of the sand falling down through the hopper. And so the integral of rho v dot n hat dA is just a mass flow rate. But now there is one little gotcha here, and that we do need to choose whether this is plus or whether it is minus. So basically which one of these two is it? Well, recall that the plus or minus sign will come from this v dot n hat. So if the normal vector and the velocity of the material moving through the surface are in the same direction, this v dot n hat will be positive. If the n hat and the v are in the opposite directions, then basically this will be negative. And so here we have n hat basically pointing up. Again, we apply the same rule. We walk around the control volume in a counterclockwise fashion, and n hat always points to the right as you are walking around to your right as you're walking around it in the counterclockwise direction, or you can think of it as n hat always points towards the outside of the control volume on any surface. So n hat points up here, and the sand's falling down from the hopper down in. So here you see that the n hat and the velocity vector are in opposite directions. So that means that for here, we choose, or we know that we choose the negative sign for m dot. And of course that's the sand falling down, so that's just m dot s. So the entire surface integral here, this nasty looking surface integral just turns into rho v dot n hat dA. That just equals minus m dot of the sand. Okay. Then we do have this other integral here, so I will work with that. And just note that this is the integral of rho dv is just the mass inside of the control volume. Okay, so now we work with that. So then partial t of the volume integral of rho dv, this equals the mass of the sand plus the mass of the air, and we'll assume that this is small. So that goes away. So this equals partial t of the sand mass, which I'll just call that ms. Okay, and the quantity of mass in the control volume is actually not a function of space, it's only a function of time. So that would be dms dt. Okay, which basically means that the amount of mass of sand in the control volume is only a function of time. So now we can put this all together here. So we have partial t of the integral of over the control volume of rho dv plus the surface integral of rho v dot n hat dA is equal to 0. Well, we substitute in our results here in here for the surface integral. This implies that the time rate change of sand mass dt minus the mass flow rate of the sand falling down through the chute is equal to 0, or this implies that the time rate change of sand mass in the control volume is equal to the mass flow rate of the sand falling through the chute. And this should not come as a surprising result. It should be fairly intuitive that basically the growth of the mass in the control volume is just the mass flow rate of the sand falling through the top. Okay, because we don't have any mass of sand leaving anywhere, and we don't have any additional sources. Okay, and even though this is a fairly simple case in your guys' homework, I do expect you to show all of these little steps. So I guess we've exhausted conservation of mass, and we're asked to find forces, so now I suppose it's time to work with conservation of momentum. So now, work with momentum. Okay, and as always, I like starting from the generic form and then just crossing out the terms you don't need. One of the reasons I like doing that is I'm not trying to be mean or extremely picky with that, but if you think of all the different forms of conservation of momentum for a control volume, for all the different cases, there are quite a few of them. And so that is a lot to remember, and it's a lot of potential mistakes. But you only have to remember one of them. And you can start from the general one and just cross out the terms you don't need. And I find that personally to be a lot easier for solving problems. And after you get used to doing that, I think you will too. There's a lot less to keep track of. There's a lot fewer mistakes, and also it forces you to make your assumptions and understand what the problem and understand the problem, to know what assumptions you have to make so that you can cross out the appropriate terms in your governing equations. So our sort of more, at least for this class, the most general conservation of a momentum equation that we will be working with is given by the time rate change of the velocity of the control volume relative to the stationary reference frame times the mass in it, which is the integral of rho dv, plus partial t of the volume integral of rho times the relative velocity vxyz dv, plus the surface integral of the relative velocity vxyz rho vxyz dot n hat dA equals the sum of the forces acting on the control volume. Okay, and so we can start crossing out terms here. Well, we have a stationary control volume, so it's not accelerating. So we have a non-accelerating control volume. And I argued above that Vxyz equals V hat, and I'm not going to show that again. So then what our conservation of mass turns into is slightly simpler. And we have that partial t times the integral over the control volume of rho v dv plus the surface integral of v rho v dot n hat dA is equal to the sum of the forces acting on that control volume. Okay, and so we need to do a free body diagram, and we need to evaluate these integrals. So as always, we gotta, for these problems, I like to draw a free body diagram and a control volume. And just like you may have done with dynamics, I like to have the accelerations and momentums on one side, and on the right side, I like to have the the sum of the forces. So I'll sometimes write just as a note to myself, I'll have a dp dt equals the sum of all the forces. So on this left side here, I put all the velocity vectors and things like that. So I can form the surface integral, and then I put the sum of the forces on the right. I find that if I put the fluid velocities and the forces on the same diagram, I find I always get their directions mixed up, and and when I was a student in your shoes, I was extremely prone to error. Okay, so the control volume here, which would be the thing I put on the left, that will look just like the other one. In fact, I'm just going to copy that other one over here because I'm lazy. Because that one still works. Okay, so that still works. So I know all the velocities coming in. I know the density of the sand coming in. Okay, and so this is equal to the sum of the forces. So I just going to draw the control volume itself. I'm not going to draw the conveyor again for reference. But the only forces we basically have on this, we are neglecting the air, and so the only forces that are acting on this are the belt tension that is accelerating the sand to the right, and a reaction force on the conveyor that is keeping the sand from falling through the conveyor belt. Okay, that's it. And so we are neglecting the air, which implies that P is truly equal to 0, because since we're only concerned about the sand and we are neglecting the air, because just the mass and momentum of the air will be 1,000 times less than the sand, we don't really need to consider it. Sand does not have pressure, so there aren't any pressure forces from the sand that we need to worry about. So we only have the belt tension and the reaction forces. Okay, so now we know we have all the surfaces marked up. We can go through and work with all of the terms now. The first term that I will work with will be this time derivative term. So now work with the terms. Okay, and so we have partial t times the volume of the integral of rho times the velocity dv in the control volume. Okay, and so here we are only considering the sand, so I'll just do a little subscript s here to basically let us note that we are neglecting the air, and I already justified that above. Now, this is the control volume, or this is the integral of all of the sand that is inside of the control volume. Okay, and so and now we had assumed above, to solve this problem, I'm going to scroll up, is that the sand, basically any sand instantly accelerates to the velocity of the belt in the control volume. Okay, so this basically means that any sand that is falling through the surface will eventually reach the bottom and then move to the right. So basically we can assume that essentially all of the sand mass that is inside of the control volume is moving to the right at velocity v belt. Okay, and so that is based on our assumption. So all sand in the CV moves with Vs equals Vb I hat. Okay, and that is uniform. So I'll just work this out here. That's partial t of the volume integral of the density of the sand of Vb I hat dv. Well, this is not a function of space, so we can pull that out. And also the velocity of the belt is not a function of time, so we can actually pull the Vb I hat all the way out of the integral and the time derivative, and this equals Vb I hat times partial t of the volume integral of rho dv. Well, again, this is just the mass of the sand, ms, and so this equals Vb I hat times dms dt, and we found from conservation of mass that this is equal to m dot of the sand. Okay, so this entire time derivative term here, we have simplified the time derivative of the volume integral, and we have simplified that to m dot of the sand times the belt velocity acting in the I hat direction. Okay, so and so that is what this super nasty volume integral turns into. Okay, now we need to work with the surface integral term. So the integral over the control surface of v rho v dot n hat dA. Well, again, we need to this circle here means in the integral sign we need to completely enclose the surface. So we're going to do the same thing we did before, and we're just going to walk around the entirety of the surface. We had the integral over the first area, and so that would be v1 rho 1 v1 dot n hat 1 dA1 plus area 2. And I'm just going to skip that stuff because area 2 is going to go to 0 anyways. And we also had a third area, which basically represented the conveyor belt surface. Okay, and this would be dA2, not A3. Okay, and on dA2, if we scooch back up to here, A2 again was the portion of the control surface that was exposed to air but did not have sand falling through it. Okay, so that goes to 0 because there's no sand. and A3 was the portion where the sand meets the conveyor belt, and we're assuming the conveyor belt is impermeable. So v dot n hat for that conveyor belt is 0. So that's 0 also because it is impermeable. Okay, so now this integral, it's not plus, it's equal. This a nasty surface integral, just like conservation of mass, there's only one surviving term, and we know, and we already argued that n hat would be j hat. V1 is minus the sand velocity, whatever that is falling down, j hat, and V1 here is just minus Vs j hat. Okay, so I'm just going to work with this. Typically, I would actually do the nice bookkeeping method that I've used in the other examples. But here we only have one surface that we have to worry about, so I'm not going to be that picky. So we have the integral over A1 of minus Vs j hat times the density of material at section 1, and that's just the density of the sand, times the dot product here. So that would be minus Vs j hat dotted with j hat over dA1. Okay, and so this just equals minus Vs. Okay, so we have a minus Vs here and a minus Vs here. So this turns into the integral over A1 of Vs squared rho s j hat dA1, and we're assuming uniform flow over the section where sand is falling through, and that means all of the guts of this integral here, we can pull that out. So then this equals rho s Vs squared j hat times the integral of A1 dA1. Okay. And this just equals to a rho s Vs squared j hat times the area times the cross-sectional area of the chute. Okay, and I'll just do some really light rearranging here. This will equal to Vs j hat times rho s Vs as. Okay, and what is, if we have uniform flow, what is the density times velocity times the area? That's just the mass flow rate of the sand falling through the surface, right? So if we are walking across a surface 1, which is this one right here, and we know the velocity, and we know it's uniform, and we know the density, and we know the cross-sectional area, the mass flow rate falling through the surface is just the velocity times density times the cross-sectional area. Okay, so this implies that the nasty-looking surface integral of V, rho v dot n hat dA, that is equal to the mass flow rate of the sand, Vs j hat. Okay, so now we know all of the nasty integral terms here. Now on the free body diagram, we do need to find the sum of the forces, and we can just find that by inspection. We just have the belt tension in the I hat direction and the reaction force in the j hat direction. So the sum of the forces is equal to the belt tension I hat plus the reaction force in the y j hat. Okay, so now we can put all the pieces together. Okay, and what that entails is that we have partial t times the integral over the control volume of rho v dv plus the surface integral of v rho v dot n hat dA is equal to the sum of the forces, not the sum of the m's, the sum of the forces. And so we can basically substitute in our result. We had that this volume integral here, that turned into the belt velocity times the mass rate of the sand falling through. That acted in the I hat direction, plus the surface integral term, and then that was the velocity of the sand falling down through the control surface times the mass rate of the sand in the j hat direction, and that is equal to the belt tension in the I hat direction plus the reaction force needed to keep the sand from falling through in the j hat direction. And this is a vector equation, so we can gather components, and we find that the belt tension is equal to the mass rate of the sand times VB, or the belt velocity, and the reaction force is equal to the mass rate of the sand times the velocity of the sand falling through the top. Okay. Okay, and so that is basically what this turns into. And I will note that you get the same result if you choose a small CV that looks something like this. So we have our little conveyor here. I have the sand falling down. And if I choose the control volume to be small, and I assume that there's always sand leaving it, so the exact opposite assumption, you can repeat the analysis for this control volume where I have the sand falling down, and the control volume is small. What you'll find is that here, this control volume, it will be steady, and you can go through the exact same procedure that I did, but only we choose the steady control volume, and so there will be a constant mass of the sand in the control volume, and we can just go through the exact same procedure, and you will wind up with the exact same forces acting on it. Okay, because the belt tension, if we're neglecting friction, should be independent of the control volume that we choose. Okay, and so that's it for this example problem, and I'll be doing quite a few more with conservation of momentum, because these problems, as you're getting used to them, can be quite tricky.